Our last video showed an isomorphism mapped the elements from one group onto the elements of another group. It was one-to-one and onto. Plus, this mapping preserved the group operation obeying this equation and mapped the identity to the identity and inverse to the inverse. In this video, we'll identify the family of some of the groups we've learned and provide two more key examples of groups used in abstract algebra. First, the familiar D6. The group of rotations and reflections of an equilateral triangle. We saw 6 elements in this group, but the triangle is only one of many polygons. We could easily look at the group of rotations and reflections of a square. By identifying the corners and following the twists, see if you can figure out how many elements would be in this group. And this introduces the family of groups because we could rotate and reflect any n-sided polygon. Second was the powerful group of permutations. We previously saw S3, the permutation of 3 objects. But there is also a family of groups here as well. We could have just as easily chosen 1, 2, 3, 4, 5, or more. And again, there's always a related n-sided polygon. Careful, don't automatically think there's an isomorphism between the n permutations and n polygons, because once we get higher than D6 to S3, we introduce a limit or constraint, and we'll cover that in a later video. Third was our group of modulo integers, and we used 12 because it was something we used every day. It's how we tell time. And remember, just like adding time, 6 plus 8, we get to 2, each element also has an inverse, such as adding 10 to 2. We get back to the identity. Again, here is a family because we could use a 24-hour clock, or 360 degrees in a circle. Any number would work, so there's an infinite number of family of these. Now, the basis of our modulo integers was simply the infinite number line. But where's the family here? Well, what if we add another number line, like we do when we describe the position on the xy plane? And we don't have to stop at x and y, we can also add z, and let's get a better look at this in 3 dimensions. Positive x to the right, as far as we can go. Positive y going away off to the horizon. And positive z all the way up to the ancient Greek heavens. And in each direction we have a unit vector. A vector that is length of 1, and it's independent of the other vectors. Like we saw in previous video, we just add the length of vectors. 2x is a vector 2 units long in the x direction, and adding 2x more just gives us 4x. Then without changing the distance on the x-axis, we can also add 4 units in the y direction. And now the vector goes from the origin to the spot 4x, 4y. That is the vector 4, 4. Remember, we have 3 axes. Without changing the distance in the x or y direction, we can also add 4 units in the z direction. The vector now goes from the origin to the spot 4x, 4y, 4z. We could do this to any spot. Just as easily go to the spot 1x, 5y, 4z, as we see here. And we can get there by adding or subtracting a number of unit vectors in each direction from any other vector. So, under the operation of addition, this certainly looks like a group. But what about an inverse? Well, for each vector, there is a vector of equal length in exactly the opposite direction, and adding these two together would put us back to the identity, the origin. So a vector space of integers in any dimension is a group under addition. The family here is just the addition of another dimension. Finally, like the vector space with integers, for our last group in this video, we're going to again be a little bit mathy. Remember the equation for a line, ax plus b? X is a variable, and let's say that both a and b are integers. As it turns out, if we have just integers, then the set of all line equations with integer coefficients is also a group. ax plus b added to cx plus d is a plus cx plus b plus d. And since both a plus c and b plus d are again integers, e and f, the set is closed. Just like the addition of integers, we have inverse numbers, those that are negative. The identity is simply 0x plus 0, and we know integer addition is associative, so the set of all line equations with integer coefficients is a group. Just like adding another dimension to a vector space, what if we added another variable such as x squared? We then have the set of all polynomials of the form ax squared plus bx plus c. Again, with integer coefficients, like we did when adding line equations, adding higher degree polynomials is still simply adding the coefficients, which gives us more integers. So even adding more powers of x with integer coefficients, we still have closure, we still have the identity, we still have inverses, plus we know, again, addition is associative. And we can make the polynomial of any degree we want. The same rules hold true. So in this video, some of the families of groups we saw were the symmetry groups, the reflections and rotations of an n-sided polygon, the permutation groups, the permutation and mapping of n objects, modulo addition of integers, vector spaces with integers, and the polynomials of any degrees with integer coefficients. In our next video, we will cover a feature of the homomorphism that measures a degree of the one-to-oneness of the mapping of phi, the characteristic known as the kernel. We hope to see you in that video, and if you like these videos, please give them a thumbs up or comment down below and help the channel grow by telling a friend or becoming a subscriber.